The first article that we want to discuss today is Gaussian elimination. And the goal here is to get a triangular system of equations, not rectangular, I'm sorry, triangular system of equations. And then we'll do that by forward elimination, and then we'll find the values of the unknown variables by backward substitution. So it's forward elimination and backward substitution. So let's start with the same example that we were doing last time. So we have 2u plus v plus w equals 5, 4u minus 6v equals minus 2, minus 2u plus 7v plus 2w equals 9. So unknowns are u, v, and w. And if you recall, we had u equals 1, v equals 1, and w was equal to 2. So let's see whether we get the same answer or not. So we need to find u, v, and w. And we want to do elimination. So obviously we want to get rid of the coefficients here, coefficients here, coefficients here, coefficients here, coefficients here, and we want to make this 1, we want to make this 1, and we want to make this 1. So let's see how do we do that. So 2, 1, 1, 5, 4 minus 6, 0 minus 2, minus 2, 7, 2, 9. So the first thing we want to do is we want to get rid of this 4. So we say minus 2 row 1 plus row 2. And then we want to get rid of this minus 2. So we'll get rid of this minus 2 by doing row 1 plus row 3. So we'll do one operation at a time. So the first row remains unchanged. 2, 1, 1, 5. Minus 2, minus 4 plus 4 is 0. Minus 2 minus 6 is minus 8. Minus 2 plus 0 is minus 2. Minus 10 minus 2 is minus 12. 2 minus 2 is 0. 1 plus 7 is 8. 1 plus 2 is 3. 5 plus 9 is 14. Now I want to get rid of this 8. So I can get rid of this 8 by adding the row 2 and row 3. So we say row 2 plus row 3 will give me 2, 1, 1, 5, 0, minus 8, minus 2, minus 12, 0, minus 8 plus 8 is 0, 3 minus 2 is 1, 14 minus 2 is 2. So this system of equations straight away gives me w is equal to 2. This implies w is equal to 2. So I can solve this one. So what I'm doing is I'm doing forward elimination. So it's forward elimination. And then I can do backwards substitution. So I can substitute the value of w here and get v here, and then I can substitute the value of v and w over here, and I can get the value of u from here. So let's do that. So w is equal to 2. So if I substitute the value here, it's minus 8v minus 2w equals minus 12, or minus 8v equals minus w plus 2w, which is equal to minus 12 plus 4, which is equal to minus 8, or this implies v equals 1. So V is equal to 1, W is equal to 2, and then we substitute. So substitute V and W here. So substitute V and W in here. So from here to here, substitute W, and then you substitute V and W. So this is backward substitution. It's called backward substitution. It's just a fancy name of how to evaluate this thing. So if I look at this equation, this is 2U plus V plus W equals 5, or 2U equals 5 minus V minus W, which is equal to 5 minus 1 minus 2, which is 2. So this implies U is equal to 1, which is exactly the same result that we got before. So if you look here, this is a triangle. This is a triangle, and this is a triangular system of equations. This is a triangular system of equations. Okay. Where does this elimination break down? So breakdown of elimination. Obviously, we cannot divide by 0. So breakdown of elimination. What are these called? These are called, this one, so the first non-zero element in every row. So these ones, maybe I write it using the red one. So this one, and this one. First non-zero element is the pivot. In a triangular system of equations, first non-zero element is the pivot. So in here we have a, so in this example we have a full set of pivots. We have a full set of pivots. Okay. When there is a full set of pivots, there is only one solution. There is only one unique solution. Why? Because the system is non-singular. However, if a 0 appears in pivot position, then elimination has to stop. System might or might not be singular. Let's look at this example. So U plus V plus W equals some number, and then I have 2U plus 2v plus 5w equals some other number, and 4u plus 6v plus 8w equals another number. If I do some row operations, I do minus 2 row 1 plus row 2, and I do minus 4 row 1 plus row 2. So if I do minus 2 row 1 plus row, so the first equation remains unchanged, u plus v plus w equals some number. So when I do minus 2 here, plus 2, this becomes 0, 0. Minus 2 minus plus 2v is 0. Minus 2 plus, so this becomes 3w equals some other number. And when I do minus 4 plus 4, 0. Minus 4 plus 6v, this becomes 2v. So minus 4 plus 6 is plus 2. Minus 4 plus 8 is plus 4. And this is some other number. We don't care. What we can do is we can do an interchange of rows here. If we do an interchange of rows, if I do an interchange of rows, I can still save my system. So if I do that, I have, so this implies then u plus v plus w equals some number, 2v plus 4w equals some number, and then 3w equals some other number. So this is a cured triangular system of equations. Triangular system of equations. And we'll see in a little while how do we do an interchange of rows. For interchange of rows, we need some permutation matrices, and we'll see in a little while how do we do that. Okay. Let's look at another example, same example, and I'll just change this number over here, and let's see what happens. So example again, u plus v plus w equals some number, 2u plus 2v plus 5w equals some number, 4u plus 4v plus 8w equals some number. So again, if I do minus 2 row 1 plus row 2, and I do minus 4 row 1 plus, this is 4 row 1 plus row 3. Minus 4 row 1 plus row 3. The first equation remains unchanged. The second one becomes minus 2 plus 2 is 0. Minus 2 plus 2 is 0. Minus 2 plus 5 is 3. So 3w equals something. Minus 4 plus 4 is 0. Minus 4 plus 4 is 0. Minus 4 plus 8 is 4w equals something else. Now, if 3w equals, let's say, 6 and 4w equals 8, this implies w is equal to 2, and we have w is equal to 2 and w is equal to 2, and we have infinitely many solutions. Infinitely many solutions. Why many solutions? Infinitely many solutions because there are two unknowns, because both these equations give you the same answers. The only thing left is this one. So there are two unknowns, u and v. There are two unknowns and one equation. Obviously, you're going to get infinitely many solutions. Okay, and if 3w equals 6 and 4w equals 7, this implies this is an inconsistent system. Inconsistent system, or no solution exists. Or no solution exists. Again, these are the singular cases that we have already discussed before. Okay. We already know, let me just briefly tell you about matrix notation and matrix multiplication. Matrix notation and matrix multiplication. So we already know matrices of same dimension same dimension means implies same number of columns, rows can be added. Obviously, you cannot add a 2 by 3 matrix to a 3 by 2 matrix because although the number of elements in them is there in both the matrices is 6, but the number of rows in the columns are different. So matrices of same dimension can be added if you multiply a matrix by a scalar, then all entries of the matrix are multiplied by that scalar. This is the example that we did when we multiplied the vector by some scalar 1 or 2, and we saw every entry was multiplied by the matrix. Okay. And if we have a square matrix, then the number of equations is, we've already covered this one, so I don't think so we need to cover this one again. How do we do matrix multiplication? So how do we do matrix multiplication? So before we do matrix multiplication, there are two ways of doing matrix multiplications. Maybe there are three actually. What happens if you multiply a row? What happens if you multiply? These are things that you already know from your high school. What happens when you multiply a row? So multiply a row by a column. So multiply a row vector and a column vector. Obviously, you cannot multiply. Actually, you can do both. So if you multiply a row vector by a column vector, so let's see, you have 2, 1, 1, and you have u, v, w. So this is a row vector. It's a 1 by 3 vector. This is a column vector. This is a 3 by 1 vector. So what do you get? So you know from your high school, you take this row and you multiply it by this one in this order. So you have 2 times u plus 1 times v plus 1 times w, and this is equal to something. This is called the inner or scalar or dot product. What happens if you multiply a vector by a column vector by a row vector? So if I do this, so u, v, w, 2, 1, 1. What do you get? So this is 3 by 1. This is 1 by 3. Obviously, we can do multiplication. So this is 3, 3 cancels. So we have a 1 by 1 scalar. So 1 here, 1 here. So 1 by 1 is a scalar. So obviously, this is a scalar. This is why it's called an inner or a scalar or a dot product. Now you have a 3 by 3 matrix. So this is u multiplied by this one. So it's 2u, u, v, 2v, v, 2w, w. So all rows, so note, all rows are multiples of the row vector. All rows of the matrix, obviously, all rows of matrix are multiples of the row vector. And you'll see, and if you do a reduced row echelon form on this operation, you'll see, so this implies there is only one independent row or column, whatever you want to call, one independent row or column. And we'll see in the second chapter, this is equal to rank is equal to actually one pivot, equals to one pivot, and this means this is equal to a rank 1 matrix. So you need to wait until chapter 2 to see what is the rank of matrix, but we know the pivots. So this system has only one pivot, and obviously this will have infinitely many solutions. Okay, if you want to solve it. Okay, so let's multiply a matrix by a vector. So there are two ways. There are one you are actually already familiar with. There are two ways of multiplying a matrix and a vector. And you should note that we can easily generalize this to multiplication of matrices. Why? Because the matrix is a collection of column vectors. Two ways of multiplying a matrix and a column vector. Okay, the first one is by rows, which we have been doing so far. So let's say we have A times X equals, so A is some matrix 1, 1, 6, 3, 0, 1, 1, 1, 4, and X is some column vector 2, 5, 0. Okay, so this is equal to, so what you do is this row times this column would give you the first one. So let me write it down. So this is 1 into 2 plus 1 into 5, 1 into, so this is actually a 3 by 3 into a 3 by 1. So this is going to be a vector, 3 by 1 vector, 3 by 1 vector. So 1 into 2, 1 into 5 plus 6 into 0. Plus 6 into 0 equals, and we'll see what that is, 3 into 2 plus 0 into 5 plus 1 into 0, and we'll see what this is. And then lastly, it's 1 into 2 plus 1 into 5 plus 4 into 0. And let me quickly do this one. So this is 2 plus 5, 7. So this is 7. This is 6 plus this 6. 2 plus 5, 7. So actually this equals 7, 6, 7. So this is what you are familiar with. This is what you do. Now look at the column picture. So B, if I multiply by columns, so what does that mean? This means, look at this one. This is actually just this one. This 5 is this one. And this 0 is simply this one. This means I can write AX, the same AX, as 2, 131 plus 5, 101 plus 0, 614. What is this? This is simply vector scalar multiplication scalar multiplication and vector addition. Scalar multiplication and vector addition. Which means, so what is 131? 131 is actually first column here. What is 101? 101 is this column over here. And what is 614? 614 is this column over here. So 2 into 1 is 2, plus 5 into 1 is 5. And this is there's no contribution because of this 0. So 2 plus 5 is 7. 2 into 3 is 6, plus 0 is 6. 2 plus 5 is 7, which is exactly the same as this one, right? Maybe I don't put this as a if and only if sign, so maybe I just put both are equal to. So this is simply a combination of, so these are actually, this is an inner product, this is an inner product, this is an inner product, inner product 1, this is inner product 2, and this is inner product 3, inner product 3. Right? So these are the 3 inner products. So when you do multiplication by rows, you have inner products. When you do multiplication, same thing, but when you look at the column picture, this is simply scalar multiplication or vector addition of the columns of the matrix. So the first column is weighted by the first number here. The second column is weighted by the second number here. The third column is weighted by the third number over here. So this is simply vector addition or scalar multiplication. Okay. Or in general, I can write in general, ith component of AX or ith row of AX equals summation. I hope you know this sign. So J is equal to 1 to n. These are the number of columns. A, I, J. This is the I, jth element of matrix A. Ith, jth element of A, and then multiply by X, J. Why? Because when you're doing this, you are taking this row, right? Ith row here, you're doing multiply by this one. So J is on the top, this J's index is on the column. So this column's over here, multiplying by these rows over here, and you get this second row over here, the ith row over here. Or this one, if you expand it, this becomes AI1 X1 plus AI2 X2 plus so on and so forth plus AIN XN. Okay. Now these row operations, so row operations can be represented, as matrix operations, or matrix multiplication, can represent it as matrix multiplication. And how do we do that? Just remember matrix multiplication. So this is the caution side, note of caution here. Caution. Matrix multiplication is not commutative. Matrix multiplication in general is not commutative. This means what? This implies AB is not equal to BA. So if we are saying row operations can be represented by matrix row operation can be represented by matrix multiplications. So if we somehow change the row operation, in some cases it will work, in some cases it will not. So let's do matrix form of one elimination step. So matrix, so let me write matrix form of one elimination. Maybe this looks untidy. Maybe I'll do it again. Matrix form of one elimination step. So we'll do one step at a time and then combine all these and then see what happens. Do we get the same answer or not? Again, we look at the same equation, the set of equations. So 2u plus v plus w equals 5. 4u minus 6v equals minus 2. And we know the answer is 1, 1, and 2. Minus 2u plus 7v plus 2w equals 9. And what row operation do we need to do? We said, let me write it again. So 2, 1, 1, 5, 4 minus 6, 0 minus 2, minus 2 plus 7 plus 2 and 9. And we did 3 row operations. So first one was minus 2 row 1 plus row 2 to get rid of this 4, and then it was row 1 plus row 3. So if I do that, I'll get 2, 1, 1, 5, and then I have 4 minus 4 plus 4 is 0, minus 2 minus 6 minus 8, this is I think 3, minus 2, minus 2, minus 10 minus 2 minus 12. Then I have 2 minus 2 is 0, so I add them, just add them and replace row 3, replace row 2. 1 plus 7, 8, 1 plus 2, 3, 5 plus 9, 14. And then what we did was we said do row 2 plus row 3. So again, row 3 is now replaced, and we have 2, 1, 1, 5, 0 minus 8 minus 2 minus 12, 0, 0, 1, and this is 2. So we have this triangular system of equation which we had before. Triangular system of equation which we have for, and these are the pivots. These are the pivots. Okay. And what are the operations? So the first operation was E. So matrix E. So matrix E represents minus 2 row 1 plus row 2. And how do we represent this by the matrix? So recall here. So recall identity matrix of any order is like this. Identity matrix, let's say IN, is like this. So 1, 1, 1, and all the off diagonal elements are 0. So identity matrix means ones on main diagonal, and zeros elsewhere. So these are zeros. So these are zeros, and these are the ones on the main diagonal. These are the ones on the main diagonal. Okay, and this is an n by n square matrix. Okay, so matrix E represents minus 2 row 1 plus row 2, which means if I have this matrix over here, so I have this matrix A over here. So matrix A is 2, 1, 1, 2, 1, 1, 4 minus 6, 0, minus 2, 7, and 2. So what should I multiply over here? So that this should be equal to, let me write the answer over here. This should be equal to, the first row is the same, 2, 1, 1. The second row should be 0, 0, minus 8, minus 2. 0 minus 8 minus 2. Obviously, we're going to do the same thing on B. So when I multiply something when I multiply something with A, so let's call this E. When I multiply something with A, obviously I'm going to multiply something with B too. So 0 minus 8 minus 2, and this one remains as is, minus 2, 7, and 2. So we are only looking at this operation. Okay, so this operation will only be equal to this one, 0 minus 8 minus 2. Okay, so 2, 1, 1 over here, 2, 1, 1 over here means I should have 1, 0, 0 over here. So when I take this 1, 0, 0 and I multiply this by this one or this one or this one, I'm always picking this first row. I'm always, so 1, 0, 0 means I am picking the first row of this matrix. Obviously, since this one is the same as this one, so the last one should be 0, 0, 1, because this row is the same as this row. The only difference is in this one, and this says this is what? This is minus 2 row 1 plus row 2. So if so, row 2 is being changed, row 3 is not being changed, right? So this one affects row 1, this affects row 1, this affects row 3, this affects row 2, this affects row 2. So the only one is, what do I need to do? I need to have this 2 over here. I need to have this 2 over here. So what I do is I say minus 2. So obviously, if this affects row 1, this will also affect row 1. This will also affect row 1. This affects row 2. This affects row 3. So minus 2 times this one. So if I look at this one, this simply means I weight the first row of this matrix by minus 2, and I weight the second row of this matrix by 1, which means it's the same thing. So if I do that, minus 4 plus 4 is going to give me 0. Minus 2 minus 6 is going to give me minus 8. Minus 2 plus 0 is going to give me minus 2. So this E matrix, actually represents this one, right? So in general, let me write, so these are called elementary matrices. So let me write a definition. So elementary matrix EIJ, subtracts L times jth row obviously of A, L times jth row of A from ith row of A. This implies EIJ is kind of an identity matrix, with the only difference that EIJ contains minus L, in ith row and jth column. And if I do that, if I look at this one, this is simply E21. So this matrix E is actually E21, and this has minus 2, or this is L, which subtracts. So since L subtracts, we're just writing this as minus L over here. So what is E31? So E31 is 1, 0, 0. So in the third and 1, so this will be minus L 0, 1, 0, 1, 0. So this is actually, this implies minus L row 1 plus row 3. So the operation this represents, so E31 represents this operation, minus L row 1, maybe I write minus L nicely, minus L row 1 plus row 3. Okay. Now look at the matrix multiplication again. So now I'm going to show you 3 different ways of multiplying a matrix. So Let's look at matrix multiplication. So matrix multiplication, and just recall each matrix as a column vector in each of its column. So each matrix can be represented as partitioned column vectors. Matrix multiplication. Okay. So associative law holds. So again, recall associative law holds. Associative law for multiplication holds. For multiplication holds, which simply means A times BC equals AB into C, which simply means ABC. Okay. So associative law holds always, but the commutative law in general does not hold. Okay, so we know E times AX equals E times AX. E times AX is equal to E times AX, which is simply equal to E times B. So whatever you're going to do on E here, you're going to do on B the same operation. Also, what is A times B? So A is some M by P matrix. Obviously, B is going to be some P by N matrix. So we are going to have, let's write A as is. We're going to have A times. So when you write it like this is B in terms of partition column vectors. And these are n of these. They are n of these because this is n. And this will be equal to. So this is a matrix A, and this is only one column. If this was only one column, obviously we'll get A times B1. If you have this column instead of this one, obviously we'll get A times B2, and in this place, so on and so forth. So this is A times Bn over here. For AB to exist, this implies number of columns of A should be equal to number of rows of B. This is basic multiplication that you learn in number of rows. This is the basic multiplication that you studied in high school, where A, B, Ij. So ijth element of AB is what? This is simply the inner product of A. So is the inner product. So if you just imagine, this is the inner product of ith row of A and jth column of B. Right? So for example, AB32 is simply A31 into B12 plus A32 into B22 plus A33 into B32 plus so on and so forth. Since this is 3 here, so this is the third row. So first column, second column, third column. And since this is second column, so this is the row, and this 2 is the column. So column corresponds to B, row corresponds to A. So 2 here, 2 here, 2 here. Okay. So let's see how can we do matrix multiplication. There are 3 different ways. So let me write the matrix first. So A equals 2, 3, 4, 0, and B equals 1, 2, 0, 5, minus 1, 0. So this is 2 by 2. This is 2 by 3. So 2 cancels. So AB, this means AB should be equal to 2 by 3. So AB should be equal to a 2 by 3 matrix. If you want to multiply, let's multiply. So we have 2, 3. So AB equals 2, 3, 4, 0, 1, 2, 0, 5 minus 1, 0. So this is equal to, okay, so again do this. So this will be 2 times 1, 2 times 1 plus 3 times 5. This is the first element. Then 2 times 2, 2 times 2 plus 3 times minus 1. And then the third element will be 2 times 0, 2 times 0 plus 3 times 0. Okay. Here and here again. So this will be 4 times 1 plus 0 times 5. Second elements will be 4 times 2 plus 0 times minus 1. And the third would be 4 times 0 plus 0 times 0. Okay. Let's see what this is equal to. So this is simply equal to 2 plus 15, which is 17. 4 minus 3 is 1. This is a bracket here. This is the bracket here. 0 plus 0 is 0. 4 plus 0 is 4. 8 plus 0 is 8. 0, 0 is 0. Okay. Now, what I can do is, in terms of combination of columns. So combination of columns, so this is a combination of columns 2, 4, first column here, 3, 0, column here, right? Okay. So 2, 4 and 3, 0. So I can write this one. So let me write it here. So combination of columns of A, combination of columns of A. If I do that, so I have this matrix just here. So let me write it over here. So this is 1, 1, and then this is 2 and 4 plus 5, and this is 3 and 0. This is a big matrix. Okay, so this is the first element. So this is the first element, which is this one. Then again, I have 2 and 4 here, and I have 3 and 0 here. Do the same thing. So I say 2 is common. 2 is common here. There 5 was common here. 1 was common here. Minus 1 is common here. So I say 2. So this is the second one. 2 and 4 plus minus 1 into 3 and 0. 3 and 0. Maybe I take this thing, whole thing here, and I move it over here. Okay. And what is the third one? Third one is again 2, 4. Sorry. Third one is 2, 4 weighted by 0 and 3, 0 weighted by 0. So I'll say, which is actually 0, but does make a difference. So this is the second one. So the first one is this one. Second one is this one. And third one is again 0, 0 and 0. So 0 is weighting 2, 4 and 0 is weighting 3, 0. So this closes the big matrix over here. So now what this is equal to? So this is simply equal to 2 plus 15 is 17. 4 plus 0 is 4. 4 minus 3 is 1, 8, 0, 0, 0, 0, 0, which is same as, this is exactly the same as this one, 17, 1, 0, 4, 8, 0. So when you do combination of columns, so these are the columns of A, these are the columns of A, columns of A, columns of A. These are weighted by the numbers in B, in the rows of B. These are weighted by the numbers in rows of B. So this is combination of columns of A. What about combination of rows of B? Combination of rows of B. So combination of rows of B simply means, so this one is going to weigh this row and this row, some of these two rows. So 2 is going to weigh the first row and 3 is going to weigh the second row. So let me write this one then. So again, a big matrix. So 2 times 1, 2, 0, 2 times 1, 2, 0, plus 3 times, maybe I write 3 here, plus 3 times minus 5 minus 1, 0. 3 times 5 minus 1, 0. This is the first row of AB. And then the second one is 4 weights 1, 2, 0 and 0 weights 5 minus 1, 0. So 4 and 0. So 4, same row, plus 0, same row. And what do I get? So each individual one, so this is 2, this is 15, this is 17, 4 minus 3, 1, 0, 0, 0, this is 17, 4, 0, corresponding, you need to add corresponding elements, 8, 0, 0, 0, which is exactly the same as this one, right? And then there is a third way. There is a third way of writing, multiplying the matrices A, B. So A times B, let me write it again. So AB is actually 2, 3, 4, 0. So this is the third way. Combination of columns of A, combination of rows of B, and this one AB and B is 1, 2, 0, 1, 2, 0, 5 minus 1, 0. So take this column and this row. So this is just like the rank 1 matrices that we did. So I can write this one as 2, 4, 1, 2, 0. This is going to give me a 2 by 1, 2 by 1 and 1 by 3. So it's going to give me a 2 by 3 matrix, right? Plus, and obviously I'm going to get a 2 by 3 matrix because this is a 2 by 2, this is a 2 by 3. So obviously I'm going to get a 2 by 3 matrix. Plus the second row and the second column. So second row and the second column, 5 minus 1, 0. So what do I get? I will get 2, 4, 0. And obviously the second row is going to be a multiple of this one. So this 4, 8, 0 plus. So these are rank 1 matrices. Rank 1 matrices. Both of these. Both these are rank 1 matrices. So 15 minus 3 is 0. 15 minus 3, 0. 0, 0, 0. 0, 0, 0. So add chorus because this is also a 2 by 3 matrix. This is a 2 by 3 matrix. We can do matrix addition because the order is the same. So 2 corresponding elements. 15 plus 2 is 17. 15 plus 2 is 17. 4 minus 3 is 1, 0, 0 is 0, 4, 0 is, so 0 is no contribution here, so whatever is this one, is 4, 8, 0, which is exactly the same as this one, 17, 1, 0, 4, 8, 0. So this is exactly the same as this one. So these are three different ways of multiplying a matrix. So this one is called column times a row. So column times a row. So columns of A, sum of columns of A by rows of B. Okay. So this is a sum of columns of A times, so sum of columns of A times row of B. So this is the sum over here that we're talking about. Okay. How do we interchange two rows? How do we interchange two rows? So how do we interchange two rows? Suppose you have 2, 3. So this is an example. So you have 2, 3, 7, 8, and I want to get 7, 8, 2, 3. So obviously I'll multiply this one. So I want to pick this row first. If I want to pick this row first, I'll do 0, 1. So this will weight this one by 1, this will weight this one by 0. So obviously no contribution here, so I'm going to pick this one. And since this one is one other one, so I do 1, 0 over here. So again, 1 will go here. So this will pick this one. 0 is going to go here. It's not going to do anything over here. Yeah. So rows 1 and 2 have been interchanged. Good. This, by the way, this is a very special matrix. This is called a permutation matrix. This is a permutation matrix and has 1 in only one row or column. Has 1 in only one row or column, and also permutation matrix P also. So this is P, and this is some A. So this is PA. So also P inverse is simply the transpose. Maybe I write P capital over here. So PP, this means transpose, and I hope you know transpose. Transpose, you just interchange the rows and the columns. Okay. So we already know matrix multiplication is associative. Matrix operations are distributive. Matrix operations are distributive, which implies A times B plus C equals AB plus AC, and B into C, B plus C into D is equal to BD plus CD. And we already know this not commutative. Matrix multiplication is not commutative at all. Okay. So let's go back. Let's go back to the elimination problem and just do elimination, row elimination by matrix multiplication. So let's go back to this example and do row elimination, row reduced echelon form by the elimination matrices. So what are those elimination matrices? So again, let me write the example. 2u plus v plus w equals 5. 4u minus 6v equals minus 2. Minus 2u plus 7v plus 2w equals 9. And we know if so we can represent this one as 2 1 1 5 4 minus 6 0 minus 2 plus 7 plus 2, and this is minus 2 and 9. So don't need to write plus here, it's just simply 7. Okay. And we know what we need to do is, so the first operation we did was minus 2 row 1 plus row 2. And minus 2 row 1 plus row 2 means this implies E is 1 0 0 minus 2 1 0 0 0 1. And the second operation we did was R1 plus R3, R1 plus R3. So let's call this some matrix F. So F was, so R3 is being changed. So 1 0 0 0 1 0. So R1 plus R3, R1 plus R3. Okay. And then the third operation that we did was, if you recall, this was simply R2 plus R3. So R2 plus R3, let's call this G. So this implies G, and G is 1 0 0 0 1 0. Since we are replacing 3, so this is 0 1 1. So this is, we are affecting row 2 here, affecting row 1 here, affecting row 1 here. So row 1 means this is over here, minus 2 means this is over here, and row 2 means this is over here. So let's see. So whether I do this operation first or I do this operation first, it's immaterial. So E times F should be equal to F. So whether I do, so let's check, whether I do minus 2 row 1 plus row 2 first, or I do R1 plus R3 first, order is immaterial. Order is immaterial. This implies what? This implies E times F should be equal to F times E. So let's check. So E times F is 1 0 0 minus 2 1 0 0 0 1. This is E. F is 1 0 0 0 1 0 1 0 1. And if I multiply both of them, so 1 0 0 means I'm only looking at the first row, picking the first row. So if I pick the first row here, this is 1 0 0. This means I'm only picking the third row. So third row means this is simply 1 0 1. This means I am weighting the first row by minus 2, and I am adding to the second row. So if I do that, minus 2 here, 1 here, and 0 here. Okay, let's do F times E. So we know E times F in general is not true, but here this should be true because the operations we are doing, the order is immaterial. So F is 1 0 0 0 1 0 1 0 1. So we are replacing the third row first, and then we are actually doing the second row. So this is 1 0 0 minus 2 1 0 0 0 1. So again, if I do that, I'll get 1 0 0 means first one on the first row. So I pick the first row, which is the same as this one, same. Then I am picking the second row as is. So picking second row as is minus 2 1 0, which is the same as this one. And the third one is I'm adding the first and the third. So if I add these two, this is 1 0 and 1, which is exactly the same as this one. Okay, so order here is immaterial, but if I do EG and GE, they will not be same. So go home and look. E times G is not equal to GE. Why? Why? Because row, you need to fill in here, row has been changed. So when you have already changed a row and then you do another operation on that row, obviously the order will make a difference. Okay. Now what do we have? We have, and there is one thing that we have not done so far, or maybe let me see if I can show you here. Let me see if I can show you here. Maybe we pointed out last time. Where have we done this substitution? This one. This is an upper triangular matrix. This is an upper triangular matrix. Upper triangular matrix. And let's call this U. So we have done some operations on A so that we have reached U, right? So it's an upper triangular matrix where the elements, upper triangular matrix simply means these elements underneath the below. Upper triangular matrix implies elements below main diagonal, elements below main diagonal, elements below main diagonal are 0. Main diagonal are 0. If the elements below the main diagonal are 0, this is an upper triangular matrix. If this is the reverse, then it's a lower triangular matrix. So what we have done is, so when we do row operations, we get an upper triangular matrix. So row operations gives us, so row operations give us an upper triangular matrix U. Upper triangular matrix U, which implies if I have A and I multiply A by E, so E is minus 2 row 1 plus row 2, and then I multiply by F, which is row 1 plus row 3, doesn't make a difference if I do FE or EF, and then I multiply by G, which is row 2 plus row 3, I get some U. I get an upper triangular matrix U, right? Okay. So if somehow I multiply G inverse here, so G times G inverse is I. So if I multiply G inverse over here, so then I'll have, so G inverse times G times FEA equals G inverse times U. This is I. If this is I, so then I multiply F inverse over here. If I multiply F inverse over here, I'll get F inverse F times E times A. Obviously, I multiply F over here. So it's F inverse G inverse U. Okay. And again, this is identity. So if I multiply E inverse over here, so I'll have E inverse times E times A equals E inverse over here, E inverse times F inverse times G inverse times U. Again, this is equal to I. So we have A equals E inverse F inverse G inverse into U, and I say this is equal to, let me call this some L. This will be a lower triangular matrix because all elementary matrices are lower triangles. So this is a lower triangular matrix. So this is actually A is equal to LU. This is known as LU decomposition. Okay. If this is LU decomposition, so this means what? So this is actually A equals, so this implies A is equal to GFE whole inverse into U, which is equal to L times U. So this is L. So GFE holds, so recall again from your high school, AB whole transpose equals B transpose times A transpose, and AB inverse, we'll prove it in the next chapter and in the next lecture, is also B inverse A inverse. So order reverse. So both for transpose and inverse order reverses. Order reverses. Okay, so just remember this one. So let's find GFE and then we'll stop here. So G times F times E equals, so G is 1 0 0, the 0 1 0, F G is 1 0 1 1, 0 1 1, F is 1 0 0 because first row is never changed, and E is 1 0 0. This is minus 2 1 0. This is 0 0 1. This is 0 1 0. This is 1 0 1. So what is GFE? So GFE is simply, so I can multiply either matrix first. So let's do this one as is, 0 1 0, 0 1 1. And if I multiply these two, I will get first row as is 1 0 0, second row as is minus 2 1 0, because this is weighting the first, row, this is weighting the second row, and this is simply the sum of the first and the third. So 1 0 1 1 0 1. So if I again do, so this is weighting the first row, so I have 1 0 0. This is weighting the second row, minus 2 1 0, and this is actually adding the second and the third row. So this is the third row. So second and third, you add them. Minus 2 plus 1 is minus 1 1 1, right? So GFE is 1 0 0, minus 2 1 0, minus 1 1 1, and we don't want to, or maybe we want to do EFG too, and then we'll stop. So what is EFG? So EFG, so this represents, so GFE represents elimination, correct elimination order, represents correct elimination order, and EFG represents reversal, of elimination. And what is this reversal of elimination? And before we do that, this is a lower triangular matrix. This is a lower triangular matrix. This is a lower triangle. So all elementary matrices are lower triangle matrices, and their product is also, so product of lower triangular matrices, matrices is also a lower triangular matrix. So you can go home and see if I have 1 0 0, E is minus 2 1 0, 0 0 1, and F is 1 0 0, 0 1 0 1 0 1, and G is 1 0 0, 0 1 0, 0 1 1. This is equal to simply 1 0 0. So you can go home and check. This is equal to 1 0 0 minus 2 1 0 1 1 1. Okay. So let's stop here. And next time, let's stop here. And next time we are going to try to wrap up this chapter. Maybe the lecture is a little longer, but we'll try to finish this one. If you have any questions, you can again either send me an email or we can discuss it in the next lecture, inshallah. Thank you.